All right, let's dive right in. We're going to be exploring the hidden invisible rules of chemistry that, believe it or not, build the very world we see every single day. We're talking about going from the tiniest atomic level all the way up to the massive, indispensable things that define modern life. So, how does it all connect? Let's find out.
Just think about it for a second. We've got these incredible engineering marvels, these life-sustaining processes we depend on. But how do we actually do it? How can we be so sure a skyscraper won't just crumble into a pile of rust, or that we can reliably purify huge amounts of water? The answer isn't just in the physical blueprints. It goes way, way deeper. You see, everything is governed by this kind of hidden chemical blueprint. It's a fundamental set of rules that dictates exactly how materials are going to behave and interact with each other. And understanding this blueprint, that's the real key to modern engineering. That's what we're going to unpack right now. So, to really use this blueprint, we need to get familiar with its 4 essential tools. Think of this as your chemical toolkit. Once you master these, you can predict and pretty much control the world at a molecular level. First up is atomic structure. This is the absolute foundation. It's like a unique identity card for every single element, and its number of protons defines what it is. But, the real magic is in how its electrons are arranged. That configuration is like an atom's personality. It determines what it'll connect with and what it'll just ignore.
Next, we have stoichiometry. Yeah, it's a big word, but it's for a really simple and powerful idea. This is chemistry's recipe book. You wouldn't bake a cake by just guessing the amount of flour and sugar, right? Well, stoichiometry is how we do the exact same thing for chemical reactions, making sure we get precisely what we want with absolutely no waste.
Our third tool is aqueous reactions. Look, our planet runs on water, and so does a huge amount of chemistry. This tool helps us understand what's going on when things dissolve, like salt in the ocean or how chemicals might move through a river. It's really the key to so much of environmental science.
And finally, there's thermochemistry, the science of energy. Is a reaction going to get hot or is it going to get cold? Does it kick out energy like in a battery or does it need to suck energy in to work? This is so crucial for everything from a massive power plant to a simple hand warmer. Okay, so those are our 4 tools. Now let's put them to work. For our first case study, we're going to look at a material you probably see and touch every single day: stainless steel. Let's use our new toolkit to figure out its almost magical properties.
It's a fair question, right? We all know that regular old iron rusts like crazy if you just look at it wrong. But this stuff, it seems practically invincible. So what's the secret?
Well, a core difference is just fascinating. Pure iron is super reactive. It basically wants to combine with oxygen and water to become rust. But when you mix in a special ingredient, its entire personality changes. It puts up a shield.
And that secret ingredient is chromium. This is where our first tool, atomic structure, comes right into play. As it turns out, chromium's electrons are arranged in this uniquely stable and balanced way. It's very chemically content. Because of that special stability, the second it's exposed to air, it instantly forms this super thin, invisible, but incredibly tough layer of chromium oxide. That little shield is what stops rust dead in its tracks.
Okay, so understanding atomic structure helps us build better materials. That's awesome. But the toolkit is just as powerful for designing better processes. Let's tackle a huge one: making sure our water is safe and clean.
So, picture this. It's a classic environmental engineering problem. You've got this massive 10,000-liter tank of industrial wastewater, and it's contaminated with acid. You can't just dump it. That would be a disaster. You have to neutralize it safely. So how do you know exactly how much neutralizer to add? Guessing is definitely not an option here.
This is the perfect job for our second tool, stoichiometry, that chemical recipe book. An engineer would follow 3 simple steps. First, you measure the acid to figure out exactly how much you're dealing with. Second, you use the chemical recipe to calculate the precise amount of a base you'll need to perfectly cancel it out. And finally, you convert that number into a real-world weight you can actually measure out.
And for this exact problem, the answer is 7.41 kilograms of calcium hydroxide. See that? It's not about 7 kilos or maybe 8. Stoichiometry gives us the precise number we need to solve the problem perfectly, which prevents waste and guarantees the water is safe.
Of course, the real world always throws in a few curveballs. As this great note from our source material points out, engineers on the ground will usually add a little extra, like a 10 to 20% safety buffer, just to make sure the reaction goes to completion and to account for any little inefficiencies.
It's a perfect example of blending that perfect chemical calculation with practical, real-world engineering.
So we've seen these tools in action for building materials and for cleaning up processes. Let's just zoom out for a second and look at the big picture. Why is getting a handle on this chemical blueprint so incredibly important?
This really brings it all home. We saw how atomic structure lets us design rust-proof materials and how stoichiometry lets us purify water. And that same powerful logic applies across the board. Understanding aqueous reactions is absolutely essential for managing entire ecosystems. And thermochemistry? That's how we figure out the energy in everything from our phone batteries to rocket fuel. The point is, every single tool in this kit connects an invisible rule to a very visible, world-changing solution.
And really, that's the main takeaway here. Our modern world isn't just built on concrete and steel. It's built on a deep, fundamental understanding of the invisible chemical rules that govern literally everything around us.
And that leads to one final thought. We've used this blueprint to tackle the problems of today, like corrosion and clean water. So the real question is, as we face the next wave of challenges, things like better energy storage, carbon capture, or creating truly sustainable materials, what incredible new solutions are we going to build using this very same chemical blueprint?